Welcome. The title of today's notes worksheet is Polar Coordinate System. And today's lesson offers us an opportunity to explore an entirely different way to represent two variable quantities on the coordinate plane. And so we're going to take sort of a look at our old system, what is called the rectangular coordinate system. And then we're also now going to sort of open it up a little bit and take a look at a new system, what's called the polar coordinate system. So I think we'll start with the old and then sort of develop some of the new and then see the connection between the two. So everyone, how about this? Just on the old side here, so to speak, let's go ahead and just draw ourselves a nice rectangular coordinate plane, sometimes called the Cartesian coordinate plane after René Descartes. And as we all know, really the coordinate plane is the intersection of two axes, the horizontal, which is the x-axis, and the vertical, of course, which is the y-axis. Maybe something like that right there would do. And then, obviously, the intersection of those two number lines, of course, would be the origin. And so what we're going to do today is take a look at it from a point perspective. And so I guess what I'd have you do is just find any point on the coordinate plane. And if we need to locate a particular point, there is a descriptor for that, and that descriptor would be the ordered pair, having an x-coordinate and a y-coordinate. And just throw that into the mix. And so I think we all know this to be the case, and then I think we can write a couple things down here. Basically, we know the x-coordinate gives us the horizontal distance from the origin. So I'm going to write that piece right here. So it gives the horizontal distance. And as we all know, the y-coordinate gives us the vertical distance. So let me write that piece in. From, obviously, where they intersect, from the origin. So that is what every ordered pair will tell us. And we've kind of talked about this before, but of course the direction matters. Horizontally, positive right, negative left. Vertically, positive up, negative down. Excellent. Now, again, from a point perspective, we're going to take a look at what's called the polar coordinate system. So for right now, I'm going to have you draw sort of the same piece right here. These are going to be labeled differently in just a little bit. But basically what I want us to do is focus on a couple things. So number one, we're going to take a look at it really from an angle perspective. So everyone, if you would, give me a horizontal ray coming off there. And this is what's going to be called for us the polar axis. So horizontal there, kind of the polar axis. And then what I'm going to have you do, everybody, is find a point anywhere you'd like. Just somewhere up there would do. And what we're going to do is have an ordered pair that goes with it. But in this case, it's not going to be a horizontal and vertical, which would describe our way to get there. What it's going to do is have an angle rotating off of the initial side, that polar axis, and tracking it with the terminal side directly to the point, something like that. And so now, everybody, what I have in place is an angle in standard position, and haven't seen this before, but sort of the direct distance from here to here. And we've talked about this so many times. If I was to track a point moving around off of the initial side, it moves in a circular path. And so we call that our radius. And so as a result, everybody, two different ways to go ahead and get to our point. Instead of talking about horizontal and vertical, what I'm talking about is the direct distance and the angle measure. And so every ordered pair in the polar coordinate system is represented with an r and a theta. Excellent. So let's go ahead and just make sure my diagram is great. Everyone throw in a rotation there. Might as well do that. And that vertex, one thing I neglected, let's put that in as well as I'm just kind of thinking about it. It's not called the origin, everybody. It happens to be called the pole. So the vertex there would be the pole. And we've got our polar axis, sort of the initial side right there. And then the angle rotates around. So in this particular case, here's what we're going to write in and then move forward with this. It gives not horizontal and vertical, but it gives what I would consider the direct distance, sort of the radius of the circle. So it's the direct distance from the pole, and the angle in standard position. Okay, perfect. And so just kind of thinking about the two then, in this case over on the rectangular side, let's put it right next to it, horizontal and vertical, everybody. x and y. And here, direct distance and the angle in standard position, everybody throw an r theta in there. Perfect. And what we're going to see in just a little while as we develop the math, we're going to see great connections between these two quantities and these two quantities right here. Okay, looks good. Let's move on to our next piece. And so if we're going to talk about an angle in standard position here, it sort of helps to have a coordinate plane, and that's what you see right here, everybody, that has some of the good terminal sides in place. So we can kind of ballpark that nicely. So this is just one I put together and then pasted on for you. So the first order of business is to just get comfortable with these points. Again, remember the idea is every ordered pair is a descriptor on how to go from the pole, in this case, from a center point to a particular point in the coordinate plane. So we're going to take a look at a couple of these pieces as we go through. Starts off easy, and then a couple little curveballs I'll throw your way that we'll have to deal with. Okay, so let's talk about this piece. 3 and 45. So radius is 3 and the angle is 45. Now, one difference, I guess, in terms of plotting points from this system compared to rectangular is in a rectangular, typically you do x first and then y and you get to your point. No big deal at all. One recommendation that I would do, and I'll just do this verbally rather than writing it on the board, I would do theta first. So get the angle measure first, then talk about your radius. So I go theta first. So what I'm thinking of, just generally speaking here, here's your initial side. And by the way, these are in 30-degree increments, just the way I did my diagram for you here. So this is 30, that's 60, that's 90, etc. So 45 degrees would be on a terminal side sort of up here. I'm hoping everybody kind of sees that one as I mirror it up on my board. So that's 45 degrees right there. And so now I know that I'm on that 45-degree terminal side, and now I just have to go on a radius of 3 units. So 1, 2, 3, and there it is. So I'm going to put a part A just next to that piece, and that would be 3, 45 degrees. Again, just to reinforce, do theta first. I think it's easier. I really do. So let's go for it. Let's do letter B. I see the 120 degrees. Everybody rotate with me. 30 degrees, 60, 90. Here's your 120 right here. So there's the 120-degree terminal side. And then just a radius of 2 means 1, 2. And there you go. There's letter B. So 2, 120 degrees. All right, good. How about letter C, everybody? 0, 90 degrees. So I would go up first and foremost, 30, 60, 90 degrees. Here it is, everyone. There is your 90-degree terminal side right there. Radius of 0, though, actually just keeps us right there. Don't move anywhere from the pole. And so as a matter of fact, you can kind of see, if we may make some type of conclusion from this, you could probably see this could have been any angle at all, and I would still be at the pole. 0, anything would get us right there. So anyway, that 0, 90 degrees, right at the pole. There's letter C. Okay, now everyone, here's where the curveball comes into play. Letters D and E. And notice here's something that hasn't popped up before. I have a negative radius, a negative r. Now in the rectangular coordinate system, I've said it from the beginning, r is always positive. There's a difference already here. In the polar coordinate system, everybody, r can be negative, and the math will bear this out as we go through, but you can have a negative radius here. So the question is, how are we going to deal with it? And this is where I like my piece. Do theta first, and then I'll tell you how to deal with that negative radius. So first and foremost, 60 degrees, everybody. 30, 60. So here's 60 degrees right here. Now what the negative radius does is it changes the direction on your terminal side. So instead of going out this way, it basically flips it over, or it's symmetrical to that pole, and it goes the other way. So here's your 60-degree side, but because the radius is -4, I go the other way. 1, 2, 3, and 4. So that's where it is. It rotates it basically 180 degrees. That would be the best way to describe it. I just go through the pole to the other side, personally. But that's how it works, everyone. So a negative radius just means we go on the other terminal side. We rotate 180 degrees off of this, essentially. Okay, so there's letter D. We'd love for you to pause the video for just a moment and see if you can do letter E. Do letter E on your own. So 150 degrees, but a -5 is the radius. See if you can pull that off. Okay, well, let's see how you did. So 30, 60, 90, 120. Here's 150, everybody. And if it was a positive radius, we would stay right up here wherever it may be. But because it's a negative radius, we go through the pole and go 1, 2, 3, 4, 5. And there you have it. There's your letter E. Excellent. And you could start to see something pretty interesting about the way we can do these particular points. These were ordered pairs that got us to these points right here, 1, 2, 3, 4, and 5. But theoretically, everybody, and actually let's just take a moment for just a sec here. Look at letter A. Theoretically, now I've opened the doors up, aren't there an infinite number of ways to rotate from an initial side to a terminal side? So if I wanted to describe this point to you, could I have done it with a clockwise rotation, maybe a negative angle measure? Could I also maybe, think about it also here, could I have done something like a negative radius and bringing me over here? So sort of a terminal side here, but because it would be a negative radius, it would bring me over. Long story short, and we'll kind of see this in play as we go through, really there are an infinite number of ordered pairs that match a particular point on the polar coordinate system. And that is a fundamental difference between the two systems. Okay, and we'll definitely go through that quite a bit here. So if you're like, just not quite sure how that would work, having multiple ordered pairs for this point, bear with it, and we'll definitely look at that situation. So it does say on your paper, let's get this taken care of, and then we'll move to the next piece. It says the fundamental difference between ordered pairs on a rectangular system and on a polar system. Here's what I wrote on my paper. So in a rectangular system, your X and Y basically. So in a rectangular system, no point can be named by more than one ordered pair. Each point, one ordered pair. So no point can be named by more than one ordered pair. Okay. All right, perfect. And that would be the case, of course. Every point has a single X and a single Y that goes with it, and that is it. But in the polar system, it's a little more dynamic. In a polar system, a point can be named by, theoretically, everyone, by an infinite number of ordered pairs. Excellent. Because again, there are an infinite number of ways to rotate from an initial side to a terminal side. And now that I've opened up the doors with a negative radius, I could go rotate to a different terminal side still, have a negative radius, and get to that point. So again, if I don't do an example exactly like that piece and really solidify that today, I know it's coming up directly on the introduction to the next notes worksheet. Okay, well, let's go take a look at a couple things here. I think the primary order of business today is to just see the connections between the two systems of representing variable quantities here. So the rectangular system and the polar system. And so what we'll do is just take a little time here and plot a few points and then get a few ideas what it would look like in rectangular form and what it would look like in polar form. So here's what I did, just at the top of your page here. I just pasted another polar coordinate system there. So I've got some terminal sides in place, and you know, each circle would represent, obviously, the distance from the pole. And here's what I'd ask us to do. As best as possible, can you draw in what would be an x-axis and a y-axis? We'll just sort of superimpose that right on top there. And then, as a matter of fact, just kind of thinking out loud with this, let's throw some tick marks in there too. So 1, 2, 3, 4, 5. -1, -2, -3, -4, and -5. Just kind of like that. Try to do it nice and dark and deep. It's not easy for me to do up on my board. But same thing on the y. 1, 2, 3, 4, and 5. And then going down. 1, 2, 3, 4, and 5. And so what we'll do is just take a little time. We'll plot a few points in place, and then have you kind of estimate, and then I'll estimate, and we'll just kind of see it. And then we'll figure out a way to convert them and figure it out mathematically. So here we go, everyone. Let's start it out. I've got a couple polar, which I'm going to convert to rectangular, and then a couple rectangular, which I'm going to convert to polar. So let's take a look. And I'm going to have to estimate myself here as I'm looking at them, but I would encourage you to write down what you think it is. So let's plot a few points. Here we go. Everybody, 2, 60 degrees. Start out with that. First and foremost, hit the 60-degree terminal side. There it is. There's 60 degrees, and a radius of 2 is about right there, give or take. So put that point in. I won't put an A by it because I don't want it to get too convoluted in with all the stuff I'm drawing in here. But basically, here's what I would ask us. What do you think the x-coordinate would be? What do you think the y-coordinate would be for that particular point in rectangular form? So remember, the polar form gives us the direct distance, the radius, of course, and the angle measure. What I want now is the horizontal and the vertical. So I'm going to go ahead and just give you my guess. And then it would be great for you to write yours as well. I'm just kind of looking at mine, and it looks like it's going about over 1 and then up, I don't know, about close to 2, but it doesn't look like it's quite 2. So for me, it looks like it's really close to 1, not sure if it will be, and then close to 2. I'm going to go with 1.8. I don't know. Again, just sort of putting numbers in that I think makes decent sense. Over 1 and then up about 1.8. And that would get me right there because this is 2, and to me it looks right above it. Okay, now you have your estimation as well. I'm hoping at least we're in the ballpark there, but we'll see. All right, everyone, let's do letter B. 150 degrees and a -4 is the radius. So everyone, if you would, go to 150, which travels along here. Here's 150. And again, a positive r would keep us here, but a negative r, we go right through the pole. And we go 1, 2, 3, and 4. Okay, interesting. Okay, everyone, so now what I'm looking for is what would be the x-coordinate and the y-coordinate as a result. So I'm going to get my ordered pair ready to go here. It would be great for you to pause the video or just do it while I'm rambling up here. And let's see. So I'm going 1, 2, 3. It looks like somewhere in between 3 and 4 on a positive. So I'm going to put about 3.5. So let me make sure I get that decimal in there. And then the negative piece, so the y value, it looks like we are coming down, by the way. So I'm going down 1, 2. To me, it looks like it's just under the 2. We'll see how that plays out. I'm going to go with this. I don't know. Maybe you did one that's, in fact, I'm looking at it from a different perspective, and I would change it up a little bit, but I'm fine with that. We'll move forward. All right, so again, just positive x and a negative y, of course. All right, now everyone, let's reverse it. Let's do rectangular. See if you can come up with a good polar here, everybody. So here's what I have. -3 and 4.5. Let's go ahead and do this one together. So let's plot it. 1, 2, 3, and then 1, 2, 3, 4. Yikes. And I'm getting about 4.5 somewhere in here, right? Oh, goodness. Not sure. We'll find out. I get around right there, give or take. Tough to tell. Okay, so if that is my point, everybody, what I guess I would ask us to do is come up with a radius and come up with an angle measure. So again, pause or just do it with me, your call. Again, I would do the angle measure first, and I see it looks like it's a little beyond the 120. If I'm rotating just, the primary rotation, everyone. To me, it looks like a little beyond the 120 there. I don't know. I'm going to go with about 124, something like that. And in the radius as well, just if I'm going right out to my point, it looks like 1, 2, 3, 4, 5, and just a little more. I'm going to go about 5.1, give or take. Again, just a guess, just an estimate, nothing more at this stage. And I'm hoping you would at least agree to some, well, I'm hoping you would agree to some point that that would be it. All right, let's do one more. 2 and negative 2. So over 2, down 2, put a point. Okay, now again, so many different ways to represent this in polar form, but let's go for it. I'm going to get my angle going. I'm going to go this way. So here's 270, here's 300. I don't know. I think that's right around the 315 mark. I'm going to go 315 degrees on that. And then in terms of the radius, 1, 2, tough for me to tell. In fact, I'm a little off, it looks like, from my board there. I'm going to go about 2.6 and see what happens. Again, just estimates. And as a matter of fact, please just make sure on your paper you highlight that piece. Just estimating. What I would like for us to do, obviously, as we take the next step, is to determine it. Let's be able to convert one to the other mathematically. So if you're ready, let's do it. I go to my next board, and it says to convert. We're going to go polar to rectangular and rectangular to polar. And you'll notice the last example of this notes worksheet would be the exact same 4 ordered pairs. And then we're going to convert them and see how well our estimations are. So don't want to leave that hanging from above, but let's let it sit tight for a moment and let's develop the math here first. Okay guys, if you would, it's all trig. Give me a coordinate plane just like that and give me a circle. And we've already seen this diagram before. We've been developing this now for a while. There is a great relationship, as I've previously mentioned, between x and y and r and theta. So everyone, if you would, find a point. It's just easier to put it up here. Find a point right up there. And as we all know, well, let's go ahead and get our direct right there, just like that. There's your r. There's your theta. In fact, I'm going to go ahead and do that solid as opposed to dotted there, sorry. And drop me a perpendicular if you would. And you see a great looking right triangle form where this is the x, horizontal is the x, vertical is the y. And so we have a right triangle with our theta, and we've talked about this before. Every point has, every angle has 6 ratios that go with it, and those 6 ratios are based on x, y, and r. And so you see in a very simplistic diagram that we've seen before, you have all 4 variables that we were talking about here today with our new system and our old related together in one picture. So x, y, r, and theta. Okay. Well, I'm going to just play a couple things out over here and then be a little more formal with it up there. But polar to rectangular, this is how it works, everybody. I'm going to do a couple things first just up here. And by the way, as you all know, if I asked you for the sine of theta, sine of any angle is always a ratio of the vertical to the direct, y to r. And by the way, does everyone see that this r can maybe come up, which it will momentarily. Let me do one other thing first. Let's get one of the other primaries taken care of. So cosine of theta. If I asked you for the cosine of any angle, you would of course tell me it's the horizontal over the direct, x over r. And one more that we're going to see just come up in a little bit here, tangent. Of course, tangent is vertical over horizontal, and so it's y over x. All right, perfect. Well, guys, I'm just going to use that idea right there to fill in our blanks, and let's get this moving. So everybody, let's go for x first. If I have r and theta, can I get x? Absolutely. I take that r, everybody, bring it on up to the other side. And is everyone okay with it sitting right next to the cosine theta? And so as a result, everybody, x is, by definition, and what we have seen before, x very simply is r cosine theta. That's it. If I have r and theta, that'll get me x. And let's go back to our trig ratios. Here they are. Old news, but new context. Everybody bring that r on up, And I see, of course, that the y value is r sine of theta. Okay, so now if I have r and theta, take a look. I just do those two pieces. I think this is probably the easier of the two, by the way, in terms of conversions. That'll give me x and y. R cosine theta for x, r sine theta for y. Keep that in mind as we'll see that math come up quite a bit over the next couple weeks. Okay, now everybody, rectangular to polar. Two things we're going to have to do. So this would be given x and y, can you find r? And then given x and y, can you find theta? So here's how it plays out. Let's do the easy one first. If I have x and y, and we've definitely done this before, is there a way to get r? Well, sure. X squared plus y squared is r squared. So just a little Pythagorean theorem here. We've seen this probably written like this before, and we'll stick with it. So given x and y, that's how we get r. Given the horizontal and vertical, that gives us the direct distance right from there to there. So that one's pretty straightforward. Nice. Okay, now the other one is given x and y, find theta. And so here is the one I think we're after, everyone. I'm going to circle this on my board. Given x and y, there they are as a ratio, can I find theta? And you can see that x and y are attached really with that tangent ratio there nicely. I think we'll have to amend it just a little bit. To find theta, I'm hoping you would agree that we would do an inverse. So I'm getting this piece right here, and I'm hoping you agree on it. It's the inverse tangent of the vertical over horizontal, y over x. Now, there are two blanks for this, and there's a reason. Because we're dealing with inverses, and we've seen it before. Inverses, they can be tough to interpret. Inverses have their limitations. And so when we do an inverse on the calculator, it can only give us a certain value. So we have to actually come up with a little rule of thumb to extrapolate from there. So very simply, when the horizontal part is positive, all we have to do is an inverse tangent on this. Okay, but when the horizontal, when x is negative, we have to do a little something else. So this is just a rule of thumb you're going to have to apply. And so you have to actually get it into the right quadrant. And by the way, if we were in radians, I'm just going to put a pi below that, because pi radians is 180 degrees. So I'm just put a little pi right there. And this would occur when x is negative. So if you remember, just very quickly, and then we'll check this out, inverse tangent is defined between negative pi over 2 and pi over 2. So when you do an inverse tangent on the calculator, it can only give you an angle measure in quadrant 4, clockwise by the way, or in quadrant 1. But what happens, guys? What happens if we have a point somewhere in the second and third quadrant? Well, unfortunately, the inverse tangent can't give it to us. So we have to find a way to get it. And the great rule of thumb is very simply, whatever we get from the inverse tangent, if we do an inverse tangent and we land down here, if I add 180 degrees, guess what, everyone? It ends up in quadrant 2. And same situation, you'll see this come up as we go through our process. But very simply, if we do an inverse tangent and it gives us an answer here, but we're supposed to be down here, well, I add 180 degrees, and it gives me the angle. So this little rule of thumb really catches all the different variations that we would see. Okay. Well, let's just check out what we have. So let's do 2 polar to rectangular, and then 2 rectangular to polar. And we'll go ahead and see how we did on our estimations, or at least I'll see how I did. So everyone, let's do the easy one first. Polar to rectangular. X very simply is 2 cosine 60 degrees. Y very simply is 2 sine of 60 degrees. And that is it. I'm going to do it all in one shot here. I think we know those values, by the way. I don't think we necessarily need the calculator. I need to make sure I'm in degree mode for this. You guys do that as well. We already know, we know the exact value of cosine of 60 degrees. And we know the exact value of sine of 60 degrees. So this is 1/2. This is root 3 over 2. And then we could go ahead and take those and multiply by 2. I'll certainly allow us to just kind of use the calculator here, but let's go for it. So 2 cosine 60. Hit enter, and I get 1. 2 sine 60, and I get about 1.73ish. Excellent. So let's put that in. This is 1, and this is actually the square root of 3, just so you know, because this would be root 3 over 2, and the 2's would cancel, so you get square root of 3. So I go back. I'm going to just have to keep doing this. All right, I said about 1 and 1.8. Pretty good. I would say 1 for 1 in terms of my estimations. So 2 comma 60 matches up to this rectangular pair right here. Let's do the negative 4 and the 150 degrees. All right, let's take a look. Negative 4, 150. So the nice thing is, even with a negative radius, it still works. So I do that, and I do that. Oops. And I was thinking something else there. Sorry. Let's quickly change that for you. So negative 4 sine 150. And again, everybody, you know the cosine of 150 degrees. You know the sine of 150 degrees. This is negative root 3 over 2. This is 1/2. But if you want to use the calculator for it, that's perfectly fine. I will do that as well up here. And let's go ahead and type it in. I get negative 4 cosine of 150, enter. And then negative 4 sine 150, and enter. So we get about 3.46 and negative 2. That seems to be the case. So 3.46 and negative 2. Let's go back and check. Let's see if it was a legitimate response to what we got before. I estimated it about 3.5 and a little below the negative 2. And where was that one? Letter B. Is that somewhere? Oh, that was this one? Yeah. Oh, I definitely see it as negative 2. Yeah, my perspective now. That looks good. So about 3.46 over and then down 2. And that puts us on that point right there. Okay, 2 down, guys. 2 to go. So now it gets a little harder. We have to go rectangular to polar. 2 parts, everybody, and get very comfortable with this math right here as we're going to see it quite a bit. So very simply, Pythagorean theorem in order to get R. Start out nice and easy there. So that is going to get us R. So I'm going to bring my calculator up and move it on over. And let's see what we end up getting. So I'm going to do square root and then negative 3 squared and let's see 4.5 squared. Just be careful about squaring a negative. Must have that in parentheses. And I'll just close it off for kicks there, but ooh, what happened there? Let's bring it back up. It doesn't want to get it from here. So let's bring that up a little bit. There it is. So R is about 5.41. That's what I get right there. So 5.41. Okay, so the first part of our ordered pair, everybody, is 5.41. Now let's go ahead and get a theta. Theta, everybody, is just like this. Inverse tangent. Okay, so inverse tangent here of y over x. So 4.5 over negative 3. Now, one thing to recognize, and this is again our rule of thumb, when x is negative, as you'll see momentarily, we have to add a $1.80 on the back. Have to add 180 degrees. Only when x is negative. Doesn't matter about y. Only when x is negative do we have to add the 180. And I'll show you why that is. And by the way, just let's look at the point just so we're clear. Is everyone cool with the fact that this is in the second quadrant? Negative x, positive y. We're in the second quadrant. Keep that in mind, everybody, as we do our inverse tangent here. So I'm going to bring this on up, and I do inverse tangent 4.5 divided by negative 3. Let me just do that first, and watch what we end up getting. We get about negative 56 degrees, give or take. Can everybody visualize negative 56 degrees? We're in quadrant 4 with negative 56 degrees. Is that going to represent this point right up here? Absolutely not. So how do I go from a quadrant 4 up to the appropriate quadrant 2? Hey everybody, all you do is you add 180. And now does that look like it's a legitimate value? So I get 123, let's do it right here, 0.69 degrees. And let's go take a look. I'm going to go back a screen there. So 123 is what I said. There we go. Here was this point. And I did say, wow, it looks really close to that 120 degrees. That's perfect. So what happened, everybody, is the calculator kind of gave us, let's see if I can catch it, sort of gave us this angle, about negative 56 degrees coming here. But we needed to kind of rotate it around to get to here. And take a look. Pretty close. I was a little off on my radius, but really super close on that angle. Let's do one more. Okay, guys, so let's see how we do on this. R first. So again, get comfortable with this math. X squared, y squared, just like that. I'm going to go ahead and bring my calculator up. I've got this value, but that's all right. So square root, everybody, and 2 squared, and then just careful with that negative. I put it in parentheses just like that, and I'll close it, and I get about 2.83. So the first part should not be a big deal, should almost be second nature. Pythagorean theorem, not a big deal. Theta is the issue. So in this particular case, inverse tangent, and I'm just going to do y over x, so negative 2 over 2. Do I have to add 180 degrees here, everybody? No, I don't. No, x is positive, so I don't have to add the 180. So let's go ahead and bring this up. Actually, you know this value without us doing it on the calculator. It's really the inverse tangent of negative 1, but I'm going to just type it in exactly as you saw it there, just to make sure. And there we go, negative 45 degrees. Now, a couple things to note with this. I'm going to put negative 45 degrees, which is perfectly fine. And, you know, just kind of thinking about this particular point and our angle measure, I had said it was about 315 degrees because if you remember what we said at the beginning of this lesson is that there are an infinite number of ways to rotate from an initial side to a terminal side. If this is my terminal side right here, I could go right there. There's negative 45 degrees. That's right. Or I can go the primary way. That would be 315 degrees. Or there are others. So really, again, an infinite number of ways to pull this off. But for our purposes here, if you get this from the calculator and you want to keep it, that's perfectly fine. I'm just going to go ahead and write a 315 above. Because if I just sort of think about that as a coterminal angle, 315 is coterminal. So you see the estimations, at least mine, pretty good. I'm sure yours were just fine as well. But please keep in mind the conversions. So from polar to rectangular, rectangular to polar for right now. We'll be working on some equations in the near future, and there's some really great graphs that we're going to be creating in polar form. So that's what's ahead of us. All right, thank you very much for listening.